Welcome back. So now let's look at the new topic on compressional tectonic environment, and in previous lecture we discussed mainly on the what features we will see in extensional tectonic environment, mainly related to the normal faulting, and then we saw two examples of the paleoseismic studies also in normal faulting environment. Now coming to the new topic, that is your compressional tectonic environment. Now in compressional tectonic environment we will have the sigma 1 almost normal to the fault plane and all that, okay. And the best example of if we look at the locations of the compressional tectonic environments, then mostly we will find along the subduction zone and collision zone. So we have one here, this is the one of the best example of the compressional tectonic environment, as well as we will also see the compressional tectonic environment along with that a strike slip also in the subduction zone. So the one of the best example you can see is along this one, and then strike slip will talk when we are talking about the transform faults between the Pacific and the North American plate. Now the most widespread compressional tectonic environment are the area of convergent plate boundaries, or the great belt of active tectonism, seismicity and volcanism that releases most global seismic energy. So if we take this, then we have the maximum amount of energy, seismic energy, which is released will be along the subduction zones, that is convergent plate boundaries. And even this was earlier this is, we say, convergent and collision boundary. So these are the locations where you will see the most of the global energy has been released in this region. Okay. Now as we were talking about the subduction plate boundaries, then we have the subduction plate boundaries over here which have been marked here, or the collision plate boundary, okay. And over here then between somewhere this portion also you can see here, okay. So now let's look at the signatures, what you will be able to see in terms of the surface manifestation because of the ongoing deformation in compressional tectonic environment. So the Earth's major earthquakes have occurred along the circum-Pacific, that is ring of fire, belt of plate convergence and collision, continental collision, and the example is your Central Asia and Mediterranean region, okay, zone of continental collision which we see in India, between India and Asia. So these are the major locations where the main locations where the major earthquakes have occurred. And then you are talking about the subduction zone and collision zone in North Africa, Southern Europe and Middle East, and along local compressional tectonic environments, that is along the stepovers in strike slip environment, in some back arc regions, etc. So these are the major locations where you will have large magnitude or the earthquakes which have occurred, and these are the locations for that, okay. So style of deformation, if we take, then large magnitude earthquakes in compressional and tectonic environment produces surface rupture represented by displacement on reverse or thrust faults, okay. So this part you will have to remember, that in compressional tectonic environment mostly we are going to see the displacement along the reverse and thrust faults, okay. Surface manifestation is either in the form of scarps, folds, or by change in elevation of land surface. That means we are talking about that either we will have a very definite surface scarp which had been developed, or we will see just the folding. Okay. So you have the displacement which is, or you see a sort of an land level change, and so just the change in the elevation, okay, and the formation of the scarps here. Of course, after the erosion you will have, so you will see something like that, okay. So these are the main forms which we will come across in compressional tectonic environment, and then their representation on the surface, okay. So this you please remember that you have in compressional tectonic environment, the manifestation will be on the surface along the reverse fault in form of scarps, fold, change in the elevation. Most common structure in compressional environment will be your thrust faults. You will see most common, and that what we have experienced and learned from the compressional tectonic environment in Himalayan region, okay. Usually thrust faults bifurcates when they are projected towards the surface, and that what we call is the imbricated thrust system. So you will have, for example, if you are having an low angle thrust faults, then you will have the bifurcation of the faults which are taking place, and you will see deformation along with this, okay. So you will be able to see the bifurcation of the faults along the major one, okay. So these are termed as imbricated faults, and even we also say branching out faults. So usually this will be seen when along the thrust faults, or you can say low angle reverse faults. Then what you see is at depth, the depths of this bifurcated faults decreases until they merge into nearly horizontal plane, that is, we term this as a detachment or décollement. So if you have like the faults which are imbricated faults, they are coming and they are going to merge along the almost horizontal plane, and that is your detachment. So this imbrication will get merged along the very low angle or almost horizontal, and this plane, that is termed as detachment, and this is very common what we see in Himalaya. So the folding you will be able to see will be along this one, and then you have the so this is termed as your detachment, or you term this as an décollement. So at depth, the bifurcated, what we see here, this one, okay, I may draw with the different color here. So you can see this part here, another one is this one, and third one is this one, okay. So they merge with the main horizontal plane, that is termed as detachment. So the décollement or the detachment, usually what we term is a low angle structure, typically a thrust fault, separating more deformed rocks above from less deformed rocks. So what it shows us that you will have the more deformed rocks will be, so basically it marks the contact between the more deformed rocks. So you will have, this will be you're having more deformed rocks or sediments from, so you will have less deformed rocks over here. Okay. So this is termed as your décollement. Okay. Now, if you look at the example from the Himalayan region, so what we have is that we have a very similar structure. We have the low angle contact between the less deformed rocks, and then we have more deformed rocks, and then we have, along with that, we have again the similar features. I'll take another color. This is not coming out well, so maybe the blue one. Okay, so we have this one here, we have another, then we have this one here. So what we have is that we, along with the, there's an imbricated fault system which we see along this one. Okay. So this is your detachment, and this is termed as main detachment fault, or you can also say main Himalayan fault. Okay. This has also been termed as, in literature you will find main Himalayan thrust, okay, main Himalayan fault, you can say. Okay. So let's move ahead, and we'll discuss when we are talking about the in particularly for Himalayas. Okay. So on surface, this what I have shown earlier also, that on surface manifestation will be very similar to what you will see in the normal faulting topography. Okay. So the topography here again, you will have something like this. Okay, the profile very much similar to what the scarp we were looking in the region of like Irpinian fault, or along the one of the fault from Bulgaria. So this is an aerial photograph which we took after 2001, and this is the one of the active fault in Kutch region. So the ground photograph of this part here, this is the scarp here. So you have the profile very much similar to what you will be looking in the normal faulting environment. Okay. But in this case, this will be your up-thrown block, and this is your down-thrown block. Okay. So this will be your foot wall, and this will be your hanging wall. So that changes. Okay. So in case of the normal faulting, even with the similar topographic profile, what you see, the fault runs somewhere here, and this becomes your foot wall, and this is your hanging wall. But in this case, the fault goes somewhere down here like this. Okay. So as we did in the case of the normal faulting, so we understand the fault runs along the base of the scarp here. Okay. And that was the part which we considered, and we opened up the trench here. So, I will show in the next coming slides what we will learn, and partly I have already discussed. So, I will be quick on this part, but we will cover more from other study areas. Okay. So, after identification of the scarp, we opened up the trench here, okay, and this is the trench from Lodi. So, this part I have already discussed. So, I will just move ahead, but I would like to show that the GPR profile which we collected, the geophysical technique, but I will talk and I will take in separate lecture on this, showing that how we collect. We will talk about the principles of the GPR and what all parameters we consider to get the subsurface profile. Now, this profile has been flipped to actually show you the exact structure what we see here. So, we have the deformation which has been seen also in the GPR profile, which was collected before the opening of the trench. Now, here the trench is hardly 2 meters of depth here, but the profile goes, if you just look at the inverted here numbers, you go up to 5 meters or more than that, okay, and then fault runs somewhere over here like this, okay. And you can clearly see the deformation on the hanging wall side, okay. So, this was the interpretation of another profile which we took, very much similar to what we found in the trench, okay. Now, usually what we see is the change in the depth of the main fault or the another fault, these minor fault systems. We will have typical of what we see, the fault, flat and ramps structure, okay. So, wherever you have the flat which has been shown by yellow, and then the red one has been marked by your ramp area, okay. So, wherever you will see the ramp, you will be able to see the folding here, okay. So, we have, and then some look in the frontal part, mostly what we see is it will be almost horizontal, but it will result into the deformation which in terms of the folding. But this portion where we see the folding is the portion we mark as in ramp area, but mostly the ramp has been marked. What we see is the change in the depth. So, slightly higher depth, then those are the ramp, and you have the flat. So, you will see also the flat deformation on this. This is not much deformation will be seen, but along the ramp you will see maximum folding as it has been shown here, okay. So, you have the flat here, then getting ramp, and then this part is also a portion of ramp because folding. So, ramp and flat structure will be one of the most common along in the compressional tectonic environment. So, this is what has been shown here. So, you have the displacement which is taking place from this place, and then you have the ramp here. So, this is a flat, then you are having ramp, and then another ramp is developing over here, which results into the folding. So, this is typical of what we call fault bend faulting, or you can say folding. So, associated folding you will be able to see because of the fault bend. So, the depth, mainly what we see is the change in depth. Now, this one of course a cartoon which has been drawn taking into consideration and very geometrically flat and inclined surface along the fault plane. Whether we see similar features in field or not, let us see a couple of examples from the recent survey which we did, not very recent, but at least almost like 1 decade back, okay. So, let us see that what we are able to. So, thrust faults are commonly associated with folds, okay. So, you will find the associated deformation will be your folding. Okay. So you have the folding which has been taking place along the thrust faults. Okay. So that are produced by the movement of thrust sheets over bends in underlying thrusts. Okay. So you have the overall you will put as in thrust only. So this whole portion you will put as in thrust, but what we see is the folds are developed along the bends. Okay. So this is one example from the, of course this was the secondary deformation, but yes, if you want to understand that what type of deformation you will expect in a along very low angle fault in compressional environment, then this was the one of the best. Okay. Now one thing which I would like to say, that this exactly same thing will happen during the major faulting, and this deformation is resulted because of the 2001 Bhuj earthquake, but was not the co-seismic one. But you can use this to understand the deformation on a larger scale. Okay. So what we see here is the strike of the fault is not same. It changes over the along if you move along this one, the strike. Okay. It is not just the straight line here like that. Okay. So when we open up the trench in across that scarp, then what we found is what has been shown here. So if you carefully look at the white line here, the white line which I am pointing out. Okay. Now this is very typical of what we were talking about. So you have the ramp here, then you have a flat here, and then again getting into the ramp here. Okay. So if you I just trace this one, it goes something like this. Okay. Then it goes up. So this whitish portion is the contact of between the overriding material and the underlying surface. So this marks this surface. Okay. Before the event. Okay. I'll just remove so that you can clearly see that. So you have the typical flat, okay, ramp, flat and ramp structure. Okay. So what we see is when you are having the ramp here, so you have the because definitely it must be subsurface, it must be something like that. Okay. So you are coming out to be then flat and then again getting something like that. Okay. So this is termed as fault bend folding. Okay. So this what we see, the fold which has been developed has been termed as fault bend folding or a ramp fault. Okay. A ramp fold. So this is typical deformation you will come across in compressional tectonic environment, mainly along the thrust faults. Okay. So close up of that, if you can now clearly is visible. So this portion is your ramp, this is your flat, this again ramp, and this portion is your what we say the fold. Okay. And this plane which has been seen here, okay, this one is the pre-earthquake surface. So this block has moved in this direction along this plane. So this will become your hanging wall, and this will be your, of course this side it will come, it will be footwall. Okay, so let's see more examples from in compressional tectonic environment. So this is another view of the same area, okay, and this is the sketch here. Okay, so what we see is you have is another portion which we see is clear cut, the ramp, and then you have the flat. Okay, so what you see is the folding on the surface. So trench A, first bulge from south east wall showing typical fault bend folding pattern. A shortening of 1.16 meter was estimated in this trench. So we measured the displacement was, or the shortening was around 1.16 meter. Deformation suggests thin skin tectonics. Okay. So we have this deformation taking place in the upper part of the crust. So we can consider this as in thin skin tectonics. And if the folds are formed at the tip or the propagating end of the thrust fault. So when we are talking about that, if you are having the flattened ram, and if the folds are forming at the tip, okay, like this, okay, then those are termed as fault propagation folds. Okay. So one is what we were looking at. We have the fault bend folding, and another one is at the tip of this one. Okay. So they are termed as fault bend folding. So for example, if you have the low angle thrust fault and the fold is forming at the tip of this, okay, so we call this as an fault propagation folding. An example from one of the trench log. So you have the fault which is running here in the sediments, okay, and then you have the typical fabric of deformed fabric which you can mark here. Okay. And then further it is going like that. Okay. So you have a typical of fault bend fold for fault propagation folding at the tip of that. Okay. So I'll stop here. We'll continue in the next lecture.